All right, hi everyone, good afternoon. My name is Loreena Lee. I'm an engineer on the Gmail team. I've been working recently on performance mostly, and taking a good look at how much memory Gmail's been using.
Hey everyone, I'm John Mccutchan. I'm part of Chrome DevTools, and my focus is also on performance and memory usage.
So today we're going to cover everything from memory management basics to garbage collection, and we're going to introduce some tools and techniques to help you understand how much memory your app is using. So why is this important? So a lot of times when people talk about performance versus memory, performance wins 9 times out of 10. And this is, the trade-off that people usually say, performance versus memory, let's go ahead and use more memory.
So the idea being that the more memory you use, that the better the performance is?
Right. So people generally, if you're caching more, you're keeping more resident memory, you have less fetches to disk, so your performance is usually improved. And so, people were starting to say that Gmail was using a lot of memory. We started hearing a lot of anecdotes, of people having a Gmail tab that's using a whole gig of mem. And that seems kind of a lot, but a lot of people at the same time are like, well, who cares? You have a ton of memory. Memory's cheap. Why not just use it? But our users the time of our users is very important. So if they're spending 2 to 3 seconds waiting for their app to be responsive, that's not good. We don't want to waste their time. So we'll start using a little bit more memory, start caching a little bit more, help them get things to be more responsive. But at the same time, what's worse than having your users wait 2 to 3 seconds? Having your app crash. So this is the He's Dead Jim sad tab, and a lot of you have probably seen this before. This is the Chrome sad tab. And the He's Dead Jim variety almost always comes as an out-of-memory situation. So we're starting to hear more and more stories about Gmail running out of memory and people getting sad tabs because of Gmail. But we didn't really have any data to know how common this was. We heard our colleagues were telling us, oh, my Gmail ran out of memory again, caused my browser to crash. But we didn't know if this was something that was, only happening to people we knew. It was like their power users were having the situation, but our parents weren't really complaining, but they only get like a couple mails, a day or a week in some cases. They probably spend a few minutes on Gmail, whereas people at Google tend to spend all day getting several hundred messages a day in many cases.
A few emails a minute.
So, but we didn't have any scientific data. We only had anecdotes. We had a bunch of tools that didn't necessarily scale up to things like applications as big as Gmail. We didn't really know how to track what was leaking. We didn't know how to find the problems. And so we we're starting from nothing. So I'm talking a little bit about Gmail right now, but really this problem is universal. Running out of memory is something that everyone can encounter, and you should care, because I don't know how much you know about the Chrome process model, but this isn't just Gmail's problem. So if you see here, I have a ton of tabs open. And Chrome will normally try to open all of these tabs in their own renderer process, but that's not always possible. So Chrome has a hard limit on how many processes it will fork. And once you've exhausted that limit, it will start putting multiple tabs in a process. So
do you mean like if Gmail uses a lot of memory or some page uses a lot of memory, it might kill 5 pages?
Right. So if all of these pages are in the same process, that's why a lot of times if you do see this out-of-memory situation with the sad tab, you'll notice several of them at the same time. It's not just one tab that's crashing, it's all of them that are in that same process. So this is something that everyone needs to care about, not just Gmail, not just your app, but anyone who ends up in the same process as your app will care as well. Just like anyone who ends up in the same process as Gmail will probably be glad that we are making some effort to reduce the amount of memory that we're using.
All right, but before we can tackle Gmail's problem, it's important that we go back to basics and understand both the conceptual concepts for memory management in JavaScript, as well as the practical with V8 in particular. So let's first talk about a high-level understanding of how memory is managed inside JavaScript. So the questions I want you to be able to answer after this set of slides is, what types of values are there in JavaScript? How are they organized in memory? What is garbage and what is a leak? These are really basic questions, and I'm sure a lot of you know the answers to these already, but it's important that we have really good definitions of what these are so that we can understand both the problem and the tools. So JavaScript has very few value types. There's booleans, there's numbers, there's strings, there's objects, and then there's external data. And So you'll note that there's no arrays here, and that's actually because JavaScript as a language doesn't have arrays. They're built on top of the objects inside JavaScript. The keys are just the indexes into the array. But this is it. This is all that JavaScript has. And the way they're organized in memory is in a graph. You'll see here there's this blue node here, and this is a root node. This is outside of your application's control. Think document or window. This is created by the browser. It's there as long as your page is loaded, and you really can't do anything with it other than maybe add properties to it. From root nodes, there's object nodes, and these are JavaScript objects, and they're the only nodes which can actually reference other values inside the graph. Terminating the graph are scalar nodes, like a Boolean number or a Boolean or a number. These values cannot reference other values inside the graph. So this is it. This is how memory is organized inside JavaScript, and this is like kind of what you as a programmer can observe. You have root nodes, which are outside of your control, objects which you can extend and can reference other values, and then the scalar nodes, which can't reference anything else. So another property that values can have are retaining paths. And this is a path from the root node to the value itself. And so every value can have one or more retaining paths. And if we look at the green value in the graph, you can actually see that there's one retaining path that starts at the root node and extends along the red edge. And there's a second retaining path that starts at the root node and then extends along these two red edges. Both of these are retaining paths for the green node. It keeps the green node in memory. Without a retaining path, the value becomes garbage, and we'll get into that in a moment. So again, this is a fairly basic operation, but it's important to understand exactly how you can remove a value from the graph. So if we want to remove the red value from the graph, we could cut this edge right here from the root node to the first green node, and then the red value is garbage. If we cut this edge, it's also garbage, or we can cut this edge. Any of those three edges cut would make the red node garbage. So what exactly is garbage? Well, it's all values which cannot be reached from the root node. Or said another way, it's all values that lack a retaining path. If something doesn't have a retaining path, then it becomes garbage. Like these nodes here. You'll see that there is no path from the root node to these values. So these values are actually garbage. At some point they were in the graph, and now they're not. And at the next garbage collection process, they'll be cleaned up, which actually brings us to garbage collection. So garbage collection, the first step in a garbage collection pass is to find all the live values. And then the second is to return the memory used by the dead values back to the system so that they can be recycled later on, as we see here. So another property that every value inside JavaScript has is its retained size. And so the retained size, you can conceptually think about this as the amount of memory that would be freed if the value became garbage. And so that's the size of the value and all of its descendants, which lack retaining paths. So if we look at the yellow node in the graph, its retained size is its size plus the size of the green node. And if we pull back, the retained size of this new yellow node is both of the green node size plus itself. And if we go all the way back to the root node, the retained size is all memory being used by JavaScript. So now let's talk about a leak. So a leak is when you, the programmer, have mistakenly left a retaining path, some value inside the graph. You think that the value has no paths starting from a root node getting to it, and that it'll be collected at the next garbage collection cycle, but you've accidentally left a retaining path. So it's a program error, as all memory leaks are. So if we look at this really simple example that's kind of Gmail themed, we have an email object and we have the message field inside of it, and we assign that to be a div node in the DOM. We then want to display these email messages, so we add that div node into a display list as well. So this is what the object graph looks like after running this code. Somewhere, starting at the root node, there's paths to both email and display. And then off of email, there's a path to message. And there's a special kind of edge from message to the div node. And this is pinning a native object, an external object that's not directly related to JavaScript. But this is the way it looks. You follow the other path, you go from display, and then you have this list of div elements terminating with the div node that we just created on the previous slide.
So everything here, the green nodes are JavaScript objects, and the yellow are actual DOM nodes.
Yes, yeah, they're external to the JavaScript. So at some point later on, we're done looking at messages, and we want to just clean out the display list. So, the programmer writes remove all children, and you think, okay, all those div nodes are gone, but whoops, we've actually cached a reference from the message object to the div node. So until the email itself is removed from the system, which could take forever and might not ever happen, this div node will be pinned in memory, and we've leaked it. So in general, like the really basics of memory management in JavaScript are that values are all organized inside this graph, and they have retaining paths, and any value that lacks a retaining path has become garbage. And then there's retained sizes, and that's the amount of memory that you're going to free up when the value itself becomes garbage. So let's go from the general to the specific and talk about the way V8 manages memory and what happens during a GC pause. So the first question you want to ask yourself is, what's the cost in allocating memory in JavaScript? And it's not the call to new. Typically, the call to new is incredibly fast. And it's like it's very, very quick until you've exhausted a memory pool. And we'll get to this in a moment of what's actually happening. But at that point, the runtime is forced to do a garbage collection. And this is where all the time is spent. And it can actually take milliseconds. So if you're writing a game, you have 16 milliseconds to do everything inside of your frame. And a garbage collection pause might pause your application for 5, maybe 10 milliseconds, which for Gmail might be okay, but for some applications, it's really too long. So it's important to be aware at the pattern at which your application is allocating objects and understand how it interacts with the garbage collector. And this is what we're going to talk about right now. So V8 manages memory in 2 generations. There's the young generation and then the old generation. And by young and old, I mean how long has the JavaScript value existed for? And over time, young values get promoted to old values. So after a few garbage collections, if the value survives, meaning that there's a retaining path and it's kept in memory, eventually the value gets promoted into the old generation. So what are the properties of the young generation in V8? Well, it offers really fast allocation, fast collection, and it's frequently collected. In fact, when you're using the timeline tool and you see the GC event on it, this is a young generation collection. In contrast, the old generation offers fast allocation, but the collection is much slower. The good thing is that it's very infrequently collected, and some of the old generation's collection occurs in parallel with your page's execution. Whereas a young generation collection is really just everything is stopped, the collection occurs, and then your page resumes. Old generation mixes a little bit of collection with your page's execution. So I want to focus mostly on young generation because this is where you're going to feel the pain inside your application, and it's going to happen fairly regularly. So it's important to understand why collecting the young generation is faster, and intuitively you have to understand that the cost of the GC pause is actually proportional to the number of live objects. And because the objects are split into the young and the old generation, the young generation actually, not much survives. After a garbage collection, most of the values in the young generation don't make it. They have no retaining path because they were used just briefly and they're gone and they're not really in the graph. Whereas by their nature, objects in the old generation have survived quite a long time. So you can't expect that when a collection is triggered for the old generation that many of them are going to disappear. So knowing that the cost of the garbage collection pause really comes down to the number of live objects, it becomes quite clear why collecting the young generation is so much faster. So let's look at the young generation in action. Young generation is split into 2 semi-spaces, equally sized. There's the to space and the from space. So the to space is where values that you allocate when your page executes, like new foo, it's coming out of to space. The from space is actually just sits there not being used until later on, and we'll see what happens with it. So assuming that 2-space started off empty, and your page starts allocating some objects. It does new A, and then new B, new C, new D. Everything up until this point has been really fast, and there's been no interruption in your page's execution. But then your page calls new E, and actually it's just too big. It doesn't fit into the 2-space, and we've we've hit that threshold where we've moved incrementally closer to this GC pause, and now we've actually triggered it. So what happens is new E doesn't happen. It's kind of paused. So we're still in a state where we just have A, B, C, and D inside of our 2-space. The page is paused, everything halts, and the collection is triggered. So the first step in a young generation collection is that the from and the 2-space are just swapped. The labels to them are flipped internally. And then the live values are found. And I'm not really going into details about exactly how the live values are found, but this is the next step. Everything that still has a retaining path, still in the graph, is discovered and marked for copy. So you can see here that A and C are marked, and B and D have not been marked, so they're garbage. They're not going anywhere. And then this is where most of the time goes. It's when the live values are copied from the from space to the 2-space. So here we are, we've done the copy, we've done the collection, we've just copied the live objects from one semi-space to the next. And the from space is just recycled at this point. There's no other work done to it. It's just like ready for use next time there's a collection that needs to happen. At this point, your page is resumed, and the E object is allocated. So what you have to understand is that each allocation moves you closer to a collection. And so when Loreena was talking earlier about this trade-off between like more memory and performance, you start to see why that doesn't hold up inside JavaScript, because the more memory you use, the faster you're going to get to this pause. And that's actually where you're going to lose performance.
Right. And not only that, but the more memory you're using, the longer the pause will take. So
Yes.
the larger the heap, the longer the collection will take.
Yep, exactly. And so when the collection occurs, your application is paused. You get higher latency. Let's say the user clicks, and then right then a collection occurs. Well, the click isn't going to register for a while because we've got to go and do a big collection. So this leads to like dropped frames and just like poor user interaction in general. And unhappy users don't come back to your site. They'll go somewhere else with better performance.
All right, so now we've heard a little bit about what happens when you have a GC pause and how it all works. But let's see how we can now take what we've learned and apply some tools and techniques to figure out how we can fix it. So I mentioned that we were starting out from nothing in Gmail. We really had no idea how problematic the memory situation was. We heard our colleagues telling us on a daily basis that they were having lots of issues, but we didn't know exactly. So we wanted to start and take some field measurements. We wanted to know how bad it was for all of you. So we use the performance.memory API, and what we do is we take measurements every 30 minutes. We store them in our logs, we aggregate them, and we can graph them. And we can kind of see what's the difference between our power users, the 99th percentile, versus like our median and the people who just spend a few minutes a day here and there. So what the performance.memory API does is it returns 3 values. It tells you the JS heap size limit, which is the total amount of memory available for JavaScript. So this is the upper limit. And then it tells you the total JS heap size, which is the amount of memory that has been allocated so far, including the free space. So this is including memory that has already been GC'd.
So could you predict an I'm dead, Jim situation by seeing when total JS heap size hits the JS heap limit?
Right. As that total JS heap size gets closer and closer, you know that at some point you're going to trigger this out-of-memory situation.
OK.
And then the third value that returns is the used JS heap size. And that tells you the amount of memory that's currently in use. So this is the amount of memory that's being used by live objects in the graph. So what we did once we had this data, we were taking these measurements from a select set of users. Gmail has a lot of users. So we were able to get quite a bit of data from these users. And what we did was we took one user. We just sort of followed that user. We took a user who we knew was using a lot of memory, who was nearing this upper limit. And we followed them for 3 days. So we wanted to see what the correlation was between the memory data we were collecting as well as the latency data we were collecting. And what we found was a little bit against what our common belief of the performance versus memory trade-off was. What we found was that as the user's heap memory footprint grew, their client-side latencies were increasing also. So over to the right of each of these graphs is by day 3. By day 3, their heap size was getting very large. It was well over a gig. And their latencies, the variance of the latencies, as well as the actual values of the latency, were much, much, much higher. And so given what you've just heard about garbage collection, you can see that once the heap was large, these GC pauses were taking more and more amount of time. And so that's what you see is happening in these latencies. So some of those outliers were probably several second-long garbage collection pauses. And those are things that we want to definitely avoid. So after seeing this data, we were more motivated than ever to get things under control. So we turned to the Chrome developer tools. If you haven't used the tools before, I hope everyone in this room has at least fiddled with them a little bit. They're really, really powerful, and they're getting better and better every day. When we were first starting out, some of these tools didn't really scale to applications of Gmail size, but since then, we've forged a relationship with the DevTools team, and things have gotten much, much, much better. Now we actually find that almost anything we need the answer to, we can find in the DevTools. So to get to the DevTools, this is what we affectionately call the hot dog menu, the 3 bars you see in the upper right-hand corner of your Chrome browser window. It's the hot dog menu, tools, and developer tools.
It's not the hamburger menu?
There's hot debate.
Yeah.
So once you open up these tools, you'll see a powerful set of tools. Inside here, we have a CPU profiler. We have a heap profiler. We have timeline tools that can tell you about your events that are happening in your page, such as the garbage collection events. Also things like paint time, rendering time. All of these things you can see in the dev tools. There's an interactive JavaScript console. You can interact with your application. So they're really powerful. But right now, we're going to talk about the tools, the part of the dev tools that we use to diagnose these memory issues. So the first thing I like to do is go to the memory timeline. And this is in the timeline panel of your DevTools. And what you can do here is you can see at the top, there's actually multiple tabs here. There's a timeline, events timeline that can show you the garbage collection pauses like the screenshot you saw earlier. And then here we're on the memory panel and the memory timeline. So at the top there you see the blue, and that's overall memory. And then down below you have the ability to see 3 different counts. And right now I only have the DOM node count enabled, but you can see the document count, the DOM node count, and the event listener count. And so these will tell you over the timeline that you've recorded how many of each of these things is currently live. So what you do is you take an action or a sequence of actions that you identify as possibly suspicious. You think that there may be a leak in performing these actions. You can perform these, you start the timeline, you can perform these actions a number of times. And so in this case, we performed them like 6 times. And then there's a little garbage can button at the bottom. You can click that button, and that'll force a full garbage collection. And if you suspect that this action should not leave any DOM nodes behind, but that number of nodes is not dropping back down to your baseline, you have a pretty good indication that there's a leak. Yeah. So here we did experiment twice, just to make sure. And we see that each time we force a GC, that number of DOM nodes is not dropping back down to the baseline. So we're pretty sure we have a leak. This is an action that we've identified that should be clean, but it's obviously not.
So by clean, you mean like there should be nothing in the graph afterwards?
We expect that the action should not leave behind any DOM nodes. We think that we've cleaned up after ourselves. Yeah. So we obviously have not. So now what? So I'm really excited to introduce the object tracker, and this is brand new. This is currently only enabled in Chrome Canary that you can get now, but you need to enable the DevTools experiment, and we'll give you instructions on how to do that. DevTools experiments and then the object tracker. And this is really cool because it combines the best of both worlds. This combines the timeline functionality, like the one I just showed, with the heap profiler that is already existing in current stable channel. And the heap profiler will tell you all the objects that are in the heap at any given time. When you collect a snapshot, it'll show you everything that's in the heap that's live at a given time. But here now you can start a recording, and it'll take snapshots periodically through that recording, and it'll tell you what objects were live in that recording at any given time. Or I should say that are live that were allocated during that time. So let's look a little bit more in detail. So here at the top, you see some color-coded bars. These identify new objects that were found that were allocated during the timeline. So I said that we take periodic snapshots while we're doing this. And as you take a snapshot, it does a full profile snapshot, heap profile. And it'll look for new objects that are different from that weren't there the previous time. So here you see that there are 10 bars, and there's different colors. The blue bars indicate new objects that were found during that time that are still live at the end of the timeline.
At the end of the capture.
At the end of the capture.
Yep.
So the end of this time frame that the whole recording was taken. The gray bars show that there were new objects that were found at that point in time, but they've since been garbage collected. So by the end of the capture, those objects that are in gray now have been collected. So you can also narrow in on any of those bars to get more information about what exactly was in that difference.
Yep.
And then down below is the heap contents.
And so the heap contents is connected to the time window that you've selected. So it's
Right.
only going to show objects that are alive that are within the time range that you've picked.
Right. OK, so I know it's hard to tell from screenshots, so you probably want to see a demo. So let's see. So we wrote a simple mail-like app, since we're talking about Gmail here. In Gmail, we cache messages for better performance. So in this little demo, we have a cache of size 5. So that means that, in theory, no more than 5 messages should be in memory at any given time. So let's take a look. OK. So first, we're going to start off with our timeline. And you see that I'm on the memory here. And let's go ahead and we'll just look at DOM node count to not confuse ourselves. And let's see. I said we have a cache of size 5. One thing we should always do is refresh. Make sure you're starting with a clean slate. And we'll go ahead and read those 5 messages. So we've now filled up our cache. Let's read 5 more. And we'll do a full garbage collection.
We're going to restart recording.
Oh, yes, we do need to record. OK, so the cache is full. Let's read 5 messages. Let's collect garbage. And let's stop the recording. So you see the blue bar at the top shows you how much memory is being used. And we see these stair step, right? This shows us that this is when I click the next message. You see there should be 5 steps. And I'm pretty sure I clicked that garbage can button, but I'm not seeing the DOM node count drop down.
Yep.
So let's try it again, just to make sure. We'll record. We'll read 5 more messages. Let's click that. We'll expand it. Still, it's dropping down, but not quite as far as I expected it to. I expected it to be down to the baseline. We had our cache was already full, and we're still got some DOM nodes here. So now we're going to go over to the profile panel, see if we can figure out what's going on. So let's refresh, start from the beginning. So this new object tracker is this last one here. It's called track allocations. So this will run the heap profiler continuously and collect these snapshots periodically while we're interacting with our app. So we'll start this. And let's go ahead and read 10 messages. 7, 8, 9, 10. And we'll go ahead and stop it. So once the snapshot is loaded, we should see these 10 bars, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We know our cache is of size 5, right? So here we see the total. Let's scroll this up so you guys can see it a little bit better. So we see these last 5 messages that we read, and those are all blue. So we know that these are still objects that are live in the graph at the end of this whole timeline capture. But now we have this one blue bar, this third one here, and it's blue. I'm expecting that we only have 5 messages in our cache, and I see that there's something strange going on here. If we look at this, this message OGS data, which is our message headers, right? We actually can look here, and we can see the object count, and there's 6. And that confuses me because I expected that we had a cache of size 5. So I don't know why we still have this 6th message that didn't get collected. So we can actually zoom in on any of these bars. We can see exactly the objects that were found in the diff. Basically, this is a diff between this blue bar and the previous snapshot. We see that these objects are still live. They're showing up here because they're still live in the heap at the end of this full timeline. So if I look at one of these first ones, well, that's probably not a good one because it's got some extra code in it. If I look at one of these here that's all gray, we'll see nothing here. And this means that everything that was found in this diff of snapshot, the snapshot that was taken here. Anything new allocations here have since been garbage collected, and that's what we expect. But here we have this blue bar, which confuses us. So let's take a look. We see that there's a message August data here. We have an HTML div element that's sticking around. And so we want to kind of see what's retaining this. What's the retaining path to these objects? So we see here that the retaining path has this saved messages array. So this is index 0 in the saved messages array. And what we see here is that we actually have some extra array that's not the cache that's holding on to this extra message, and that's causing it to not be collected. And so we can actually go back to the source and look and see what this saved messages array is in this case, and go ahead and make sure that we free that reference up, and that will cause this to get collected.
Yeah, you can use the view of the retaining path down here as like a clue to where in your source code this object was allocated and where it probably should be cleaned up.
Right, right. So that's the object tracker.
Mm-hmm.
So let's go back and see, was this really worth it? I mean, this is kind of a lot of work, especially if you think about an application of Gmail size. The JavaScript is actually huge. So going through and performing these techniques actually can take some time. But was it really worth it? And I'd say a resounding yes. So this is the data that we collected using the performance memory API that I mentioned earlier. This is actually a graph of about a 10-month period in 2012. If you look far to the left, you can see that memory was actually really far out of control.
And so the scale here is just relative to the median?
Right. So it's relative to itself, I guess.
Okay.
Yeah. So the green line on the bottom is actually the median, and the blue line up at the top is the 99th percentile. So the blue line represents mostly our power users, and you can see that for our power users, we've actually reduced memory in this 10-month period by 80% or more, actually. And for our median users, it's hard to tell in this graph just because of the scale, but we actually reduced the amount of memory that our median users was using by over 50%. Nice. And you'll see like there's these two peaks on the blue line. And they're there in the other lines as well, but the scale is not quite as obvious. And what these are actually showing us is two regressions that we found that were in Chrome itself, not in Gmail.
So you found bugs in V8?
We actually did find some bugs in V8. And in these particular cases, they were fragmentation bugs. So the garbage collector was actually collecting garbage, but it was so fragmented and in these tiny little chunks that Gmail wasn't able to use them for new allocations. So what we noticed here was that we mentioned there were 3 values that are being reported by the performance memory API. And one of them was total JS size, which was the memory in use plus the free space. And then there was the used JS heap size, which was the live objects. And we noticed that the gap between these two lines was growing. So that's how we've realized that it wasn't actually a Gmail problem that was causing these two peaks. So once those were fixed, we got things back under control, and we're in a pretty good place right now. So
looks like it.
So really, what we're asking of everybody in this room, and hopefully beyond, is to really think about how your memory usage is affecting your performance. And we recall that the higher the memory footprint, the longer the latencies were and the wider the variance. And so really, these GC pauses can be a performance killer. So ask yourself these questions about your app. How much memory is your page using? Are you using an amount of memory that is reasonable for the size of your app? If you have a small, not so interactive app and you're using hundreds of megabytes of memory, you're probably not using things most efficiently.
Well, so even for Gmail, I mean, you were able to reduce memory usage for the 99th percentile by 80%.
Right.
Without impacting performance, I imagine.
Well, and without negatively impacting performance.
Yeah,
so we actually did see a modest improvement in our latencies, and so it really does make a difference. And for Gmail, the latencies are hard to tell sometimes, but for the 99th percentile, seeing a 10% improvement in latency is a big deal for us.
Yeah.
So is your page leak-free? So when you first load your page versus after a day, after 2 days, after a week, is the memory staying in a reasonable size? Is it growing over time, or are you leaking memory that you shouldn't be? And how frequently are you GCing? We showed you some tools that you can use to figure out how frequently you are GCing and if those GC pauses are affecting your performance.
Yeah, if you're seeing a lot of GCs, that probably indicates that you're just allocating a ton of objects inside JavaScript, which you likely don't need to be doing. So that's just another indicator that maybe there's a different way to structure your page or your site so that like the performance impact of GCs can be lessened.
And then we showed you a bunch of tools. The Chrome developer tools really are getting better and better every day. We have some really great documentation on developers.google.com that you can check out. There's a lot of tutorials on there that you can use to get an introduction to these tools. We'll actually also be publishing an article that goes with this talk, so you can get more information on how to enable the object tracker and try it out. We'll also send you a link to our demo so you can kind of follow along.
Yeah, you can try this out yourself. You can try the continuous snapshot technique, and the article will be available next week.
And then, there's the heap profiler. There's the object tracker that we just showed. So and play around with everything. The timeline is really cool. You can see really everything that your page is doing. When you refresh it, you can see how the page actually displays. You can get there's a lot of great talks this week that you guys should try to attend as many as you can just to get more information.
Mm-hmm.
That's it. Thank you.
Thanks, everyone. So for reference, there's a link to the demo source. You can just hit it with your browser. And here are the instructions on how to enable this object tracker today. So we can take questions, and be sure to rate the talk using the app.
Hi. So, well, in an ideal world, your application should not have memory leaks, but there's no ideal world yet. So my question is there possible to have some kind of listener with JavaScript that once your application is about to hit a memory leak, with JavaScript you will know about it, and instead of showing this sorry.gem page, you can take some actions before actually losing everything?
So for those of you who couldn't hear, the question was, could there be an event channel that kind of signals that a memory leak has occurred? Is that correct?
Is about to occur.
Or about to occur, yes. So the issue with that is that there is no way to know the intention of the programmer. So the V8 can't possibly conclude that, oh, this reference in the graph that's keeping this value here is an error, because maybe you actually intended that reference to be there. Although it would be nice to maybe have some event channels that tell you when you're getting close to the heap size or something. Yeah.
So like if you could definitely have some sort of listener that would pull this performance.memory API and sort of see that the limit is being approached. But there's not really any way that you could say, hey, you've been holding on to this thing for a long time. Are you sure you wanted to? That's actually really, really tricky.
Oh,
yeah.
Okay, thanks.
Thank you.
So in terms of the process that you guys went through last year, so obviously the example you showed here was ridiculously simple, right? So there's kind of like, okay, we have a memory leak. What did you find were the common actual sources of the memory leaks, like the kind of coding patterns that were causing them? And in a code base like Gmail, which is hundreds of thousands of lines of code, how would you just narrow it down? I mean, you have these objects, but then you need to know where these objects getting allocated and where the bad stuff is actually happening.
Right. So we had the heap profiler, and the object tracker is brand new, so it would have been really awesome to have that last year.
Yeah.
That would have made things a lot easier.
For
but
sure.
Using the heap profiler, there's a technique that you can take multiple snapshots and compare them to each other. So we kind of performed some actions, and we saw that memory was growing when we did something as simple as compose and discard. So if you compose a message and you discard it, once the undo butter bar disappears, we really expected that there should be nothing left over from that action. And so we could perform something like that and then do these comparison between multiple heap profiles, heap snapshots, and sort of see what's lingering. And in those cases, we could find certain objects, and we could look for those particular objects that were being left behind. So that was one of them. I would say we have a few different categories of bugs that we found. One of them was things like infinitely growing caches, so things where we were saving references to things that we didn't mean to. One case, we had a list of callbacks that were supposed to be invoked when a particular action occurred, and that action never occurred. So we had an infinitely growing list of callbacks. There was also a bunch of cases where we had event listeners attached to particular objects, and the event listener was acting as a reference on those objects. So the Clojure team, the reason why I didn't mention it here is the Clojure team is actually going through we use Clojure, the Clojure compiler, and they've gone through some really amazing hoops to try to eliminate this particular coding problem. And so if you do use Clojure and you do have this problem where you have event listeners that are causing references to particular objects sticking around, newer versions of Clojure should eliminate that problem for you.
Okay, great, thanks.
Thanks.
What would be the ideal size for the young space to avoid, frequent GC pause? How would you determine that?
Well, the ideal size would be infinite. You could just have it grow forever, and you'd never GC pause. It's actually very difficult to find that sweet spot of a practical number. So that's a difficult question. There's not a straightforward answer to it, I suppose.
So if I can actually
Sure,
tag this in. So in the GC pause that you showed, like freeing up two objects had enough room for E, right? If there wasn't enough room for E, in that case, would that flush to old or?
No, young generation collection occurs without an old generation collection.
But if the flushing two objects didn't have enough room for E?
Oh, I see. Yeah, at that point, you would start to fall back to we have to do a full collection and try and free memory, yes.
Cool. Thanks.
Thanks. Yeah.
Hey, so some of the graphs you showed with the Gmail performance with the different percentiles, that's actually awesome. So do you have any tips for building tools like that? Like, are there any tools that you know of that can help monitor your users, in production?
So you can actually just call the performance memory API from your application at any given time. And this is enabled.
And that's for memory and UI latency as well?
So the latency is a totally separate tracker. We have a separate tracker. We're actually out of time, but we're happy to stick around. We'll probably head upstairs to the Chrome office hours area, so we can.
So for anyone who still has questions, you can just meet us upstairs in like 10 minutes, and we'll take questions there.
But the short answer is that latency we track completely separately.
Thank you, everyone.
Thank you.
Yeah.